Hello, welcome back to class and welcome to lecture 3 in Math for Designer. Today we are going to learn about numbers and number bases and more. Oh yeah, I should also put that as a topic. But yeah, all about numbers. And there are numbers that are not just digits like 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are just things to represent numbers, but there are more interesting facts or interesting trivia, I guess, about numbers. We are gonna see them today. In the first section, we start off with something light. But to set up the keywords about numbers that you might hear somewhere, you might have seen it, but maybe they use different words. So let's define them first. And it's the tail of numbers, and what they are, where we can find them, and how we can use them. Okay, so remember that last time we talked about sets. We have this notation, the name of the set, and then we have the left bracket, left curly bracket, right curly bracket, and then you put elements or things inside the set. So from now on, whenever we talk about this set, the one with 4 elements, we can just use a single letter A. And we do the same here with numbers, because there are lots of numbers out there, and there are lots of types of numbers. So we're gonna use the set notation to denote them. We don't, you don't have to write a long sentence to describe them. So we talk about set of numbers. And the first set is should be the most familiar one, which is what we call the set of natural numbers. They are called natural for a reason, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. In nature, if you look outside your window, or just look at your hands, you can count how many fingers there are, how many hands you have, how much money you have in your pocket, all those sort of things. Those are the numbers that are natural to us. They can be represented by objects. There are 5 bears, 3 coins, 2 boxes. And so they're natural. And that's the letter N, because N is for, natural. The letter comes from. And in math, if you just write N, it just seems like a normal letter. You might not think about set. So in math, we make it fancier by adding a line to that. If you type that, there are 2 ways to write that. You can use the typing thing when you make a double line on the middle one, on the diagonal one. But if you are a math person, if you see that somewhere else, they will make the line double as the first line. But anyway, they mean the same thing. Like there's a fancy letter N that represents the set of all the counting, all the rational numbers, 1, 2, 3, 4, 5, 6, 7, and so on. We have an alternate name for it, which is counting numbers. You count 1, 2, 3, 4, 5 up until you get tired of counting. So that's the boss basic set of numbers. One thing you may notice is that even the basic one has infinite number of numbers, the size is infinite. But that's lots of numbers. We can keep counting forever if you want to. Next one, we extend the idea. Oh, by the way, this is kind of in chronological order. If you study math history, people want to hunt for bears, or want to count how many people there are in their family. Or those sort. They invent these numbers. And next, when you do businesses, when you trade, and sometimes you need to. Sometimes, but most of the time you need to have the concept of like debt, deficit, or the it's called the decrease. So we add more numbers, or we add the negative ones, and 0. We also have 0. Surprisingly, we didn't have it at first. But also, as a fun fact, in history, 0 was introduced very late. It's not, if you study like language or any kind of writing, 0 wasn't introduced in the very early stage. It was only introduced when people study like, more seriously. I think it was in 16th century or something. It's pretty. It's a human invention for the number. Yeah, but anyway, so next we have the word integers. You might hear this more often than the word natural numbers, because if you do math, usually you want to take into account of all the negative ones as well. They are important. We need them. So that's a larger set of numbers. We call it z, and z is a kind of integer in German language. There's some rule something. We should help like they use different languages. But anyway, yeah, we represent the set of integers with the letter z. It includes negative part and 0. Get more friends. And then we have even more friends. Next one, the next level is the set of what we call the rational numbers. You might know them better as fractions. The other numbers that you can write as a ratio or a fraction of two integers. Instead, the rational number is built on top of integers. You need to know integers first before you can define rational numbers. So notice that in this case, like the notation is not the common one. We talked about it before, but this is also a usual way to write a set. We write what elements look like. In this case, they look like A over B. They look like a ratio of two numbers. Then we write conditions. What are A's? What are B's? And B's are integers, and B is not 0. You can't divide anything by 0. But A can be 0. Like 0 or 1 is fine. It's just a number 0. But that's the next one. Oh, and yeah, Q is now we are back to English. Q is the case of all the quotient. Again, kind of a fancy word for fraction or ratio. But you know, fun fact, yes. And once we know these three sets, we can write them in terms of set notation. Oh, I should also add that to just apply our past knowledge. So n is a subset of z integers, and z is a subset of rational numbers. That means if you give me an integer, let's say you give me -3, that -3 is also in the set of rational numbers. And that's maybe obvious, right? -3 is rational numbers. But if you ask me why is that number is in the rational number, we say, oh, because you can divide it by 1. Now -3 over 1 is in the form, and so it is part of this set. It has the requirement we need. They are both integers, and the pi at the bottom, the denominator, is not 0. So there are 3 sets. And if you prefer fancy set, notation, maybe that's better for your understanding. You can write them as nested circles, where the smallest one or the innermost one is the set of natural numbers n. In the next layer we have z, the set of integers. In the next layer we have q, the set of quotients. And usually if you study math, you would love to ask, wait, what's next? Is there more? We find them, and yeah, luckily we can. Maybe with what is out there. Right, so The next thing is kind of weird. We have rational numbers, as you know, as a ratio. Now ratio each. Right. What about numbers that cannot be expressed as ratio? If they cannot be expressed, then we say they are not rational. Not rational. In the fancy math or maybe English, I guess, we call it irrational. That's just a or the not prefix. If it's not rational, then it is irrational. It's kind of weird, right? And then we don't have an exact definition for that. Maybe not surprisingly, because you know when you talk about things that are not in this set or not part of that, then it's difficult to express it. We would just call, you know, they are not expressible as a fraction. And if you know some math, you know that there's also an alternative definition, which is it cannot be written as a repeating decimals. These repeating decimals, you have numbers like 0, 1, 1, 1, 1, 1, 1, 1, 1, or 0, 1, 2, 1, 2, 1, 2, or 0, 5, 0, 0, 0, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. You know, also numbers. Because there is a be fun, I guess. It's a fun way, yeah, to express them as a rational. 501 repeating is 1 over 9. 512 repeating is 12 over 99. 8, whatever it is, I don't know. 5 over 9. Awesome, I guess. So if they repeat, if you can write them as a repeating decimals, then that's a way to convert them into a ratio of 2 integers. But if they can't be converted, then we call them irrational. And the notation is again kind of weird. But we sort of use this notation. Remember the idea of a complement? We have something inside the set A. We can talk about things that are not they're outside the set A. And from last time, the notation for the complement was A to the Z. Not to the C, but you know, A with the student C. The node that we talk about is complement, or maybe the A prime. That's here, and not commonly used, but sometimes used notation for complement, which is giving it a hat, a tilde on top. But that's the notation. Like, it's not rational. It's not in Q. That's what we have here. Yeah, and finally the set we use, not the last one for sure, but the set we use is what we call the set of real numbers. And real is for R, you know, so it's real. Definition is that it's a kind of the numbers that you can write as decimals, repeating or not. If you pick up your pen or pencil, and then just write random numbers, then you get a real number. Or even if you repeat them, or not repeat them, if you get write random numbers, they are still considered a real number. Right? As long as, or maybe, oh yeah, I should also add another definition, but the more precise definition of the real number is the numbers you can find on the line. You can find on the number line. But if you write a line and add some ticks or some milestones, oh minus 2, not 3. That's on all milestones or numbers. If you put your finger at, let's say, there at this point, you can say, oh, that's the number 1. If you put the finger there, maybe, oh, you can say that's number 2.5. If you talk about a number like there, maybe it's minus 0.4545 and so on. So these are all numbers that you can find on the line. You might not know the exact place, but you get an idea. Oh, it's minus 0.4, so it's between minus 1 and 0. It's somewhere here. So as long as you can pinpoint, you can indicate the position of that number, then that number is a real number. And an alternative definition, which is not helpful, is a set of all fractions and non-fractions, rational and irrational numbers. And you should, most of the time, whenever you think about solving math problems, you would end up with using the R, the set of numbers that you think of, and that will conclude the last one on the chain, I guess, on the real chain. Again, we have natural numbers n, 1, 2, 3, 4, 5, 6, 7, and so on. We have integers, the z, and plus of a whole number. And then we have irrational numbers, as q, a ratio, a fraction, and lastly we have the real number. The forces plus 1, I'm gonna add that soon. But here, if you want to get a better picture, this is what we have. So we have the set of natural numbers inside the innermost layer of this number onion, I guess. And then we have set of integers, z. And then we have set of rational numbers, q. And then we kind of have set of real numbers, r. This time I changed the notation from, I changed the shape from ellipses to rectangle. Usually this is where we stop. We consider that to be the universe, or the numbers you would usually use in your daily life, or you can see, or you can visualize, are in this box, nothing less, nothing more. Okay, so now we have this process, and the fifth one, the q, the irrational numbers or complement of q can just be, placed there. It's not in the green part, it's outside the green, sorry, it's not in this blue ellipse, outside that, but it's still in the real number, so it belongs there. And that's the image we have. Then did you have, if you ask me to place numbers inside this set, I can do so. For instance, if you give me a number 1, where do you place 1? Oh, 1 is natural number, I guess. I saw it as the first one in the list. So yeah, 1 belongs there. Maybe I should zoom that because that's probably focus. What else is in the set? Put 1 there. We can put 4, we can put 11 natural numbers. Then if you want to put something in the set of integers that are not natural numbers, you will put negative numbers, -3, -10, -9,099, and 0. Below belongs here. These numbers are integers but not natural number. And then you can go to the next layer for numbers that can be expressed as rational, but not in C yet, not integers yet. Like 1/2. It totally works. 3/4 -10/99. You name them. 10 a million over 3. Those are rational numbers. And then we have the outside of rational numbers, which are irrational. It is kind of difficult, or maybe not that difficult, but there are some numbers of this form, but it's rare. Like you have to put something like square of 2. If you have some, if you know some trivia about square of 2, then you will know that that is approximately 1.414 and so on. And the reason we say approximate is because the decimals are not repeating. They are not repeating. You can't find a pattern in the decimals. So there's no way we can express them as fraction. And if you enjoy math, you might have heard about the proof that square root of 2 is not rational, which will involve doing math, of course, involve trying to prove that it is impossible. It's never a ratio of two integers. But yeah, that's a story for another time. For now, we have square root of 2 there. We have pi, our favorite number. Is it? We have e. That is a weird but it's very important constant. It's about 2.71. 0.718. That's a number that shows up as an exponent. Will you encounter at some point in this course? You know, there are lots more, but it is, let's say, impossible to come up with your own. There's a fee, the current ratio. That's like, I don't know. Even I can't do that. But that's the map, I guess, of all the numbers we use. We give them names. And also in terms of sets, notations that you can use to make your homework or your writing, wherever it is, shorter. But these are all the numbers that we, again, need for this class. But the question is, of course, is there anything else outside? Is there any number that we cannot express or cannot write written as a decimal? Sure, there are more. If you know this famous number, the square root of -1. And that's a real number, because if you know for a fact, if you take a number that's squared, you always get a number that is positive or 0. So it's never negative. There is no such number that you can square and get -1. This is what this number is. But if that number exists, then its square must be -1. But it's not. No, there's no such number. And since it's not real, we call them imaginary number. Imaginary number. Which again, I can teach you, the whole semester all about this number, but you wanna just, it's good enough to know that it or they exist. There. So that's one way to invent or create new numbers outside the real numbers. And just in case, it's just more like a trivia. So if the irrational numbers are pretty big, rationals are the ones that you can express as decimal, as a ratio. Right? But what is not that? And what does it mean for a number to not be expressed as a ratio? The answer is a lot of. It's not easy to define them, let's say. But I can give you some examples here, right? There's a name. Actually, this is a set. It's somewhere there. But we can actually make several types of them. And we group them into different types of irrational numbers. Algebraic numbers. These are the numbers that you see sometimes in your life. Maybe not a lot, but they exist. And there are some fancy numbers called computable numbers. Computable means you describe what it looks like or what it represents. You just put it into a computer. If you do output the number, but it's not gonna be able to output the exact number, because again, if you write it as decimals, they are not repeating. So the computer would have to compute decimals forever. It's not pattern. it never repeats. So yeah, it's going forever. But at least we have let's say a close formula for that. If you have enough patience, you can compute those numbers or as precise as you want. Maybe 1,000 digits, 1,000 decimal digits, 10,000s, millions, billions, trillions,
and so on and so forth.
And there's a weird number that you shouldn't go there. You shouldn't touch that. That's dangerous. But yeah, there are more things out there. Oh, then I heard this meme. What's the showy dark place? Oh, there's no computable numbers. You must never go there. So yeah, please don't. Maybe just for fun. And yeah, that is it. That's complex numbers. Again, we don't need this for our class, but good to know. Just in case. And interestingly, these are all the numbers we can invent or we can think of. It's more like it's either real or not real. It's just a single number or a number times an I, or combination of those two. But nothing else. In terms of computation, in terms of problem solving, these are all we want. Or all we can ever invent. But there are more, because sometimes when you talk about numbers, you don't talk about, their structures. Oh, it's integers, irrationals, that's the math part. Maybe you are more into the recreational part. You study numbers for fun, for, just for fun. It won't, give you food. You have to do something else to feed your family. But yeah, let me go here first. You can define numbers in different ways, right? You can define Fibonacci number. There's a famous one where you start with 1 and then 1 and then the next. And then each number after the third one is the sum of the two previous one. 1 plus 1 is 2. 1 plus 2 gives you 3. 2 plus 3 gives you 5. And so on and so forth. And you kind of see Fibonacci numbers everywhere. You might recognize this meme or this famous or infamous spiral shape. Oh, it's everywhere in nature. How the wave works, this is how. And scroll, this is how. Bees make their lives. All those fancy stuff. And sometimes you have something like a triangular numbers. And interestingly enough, like the definition is kind of simple. But you will hear this a lot if you this design a board game. I'm not sure about computer games, but if you design a board game, you're gonna hear this word a lot. Because that's one of the tools that you can use to make a scoring system balanced, interesting, fun. So that's the sum of the first n numbers. T1 is just a single number. T2, you get 1 plus 2, but T3 you get 1 plus 2 plus 3. And the first one you get 1 plus 2 plus 3 plus 4, and so on. Yeah, important or famous, or let's say useful numbers you might use at some point. And then we have you have up there. There's a link to clip. Let's see exactly what we call this fascinating trips to number stuff. This is a snapshot, right? Oh, there are numbers. They have this rough size. But if you go to the clip, you will see like plot twist. Actually, this like black circle is like the whole thing. If that's a real number, then this black circle would like span over the whole real numbers. Roughly, just to give you an idea of how big these things are. But they can't be compared. But yeah, that's numbers. You can find out more if you watch that clip. We have these two numbers, and lastly, we have some exotic numbers. That's real numbers. You might have seen that somewhere if you want to code some three-dimensional games or three-dimensional object. Because if you want to rotate an object, you have this ball. Let's say like this creature. You want to rotate it around, right, up, down. Or you want to rotate your camera. There's a camera.
There's not a camera, but yeah, suppose
It's a camera. And you want to rotate it to get a different angles, different views. Then you need to compute how they move. What's the view or the angle
they are pointing
looking at. And so yeah, we need to define this number, which is called the quaternion. And pretty fancy, which is I would say bizarre. But believe me, this is very useful when you want to compute three-dimensional rotation. And again, we don't need to know that now. Just
in fact.
so that's a fun fact. Now we have some quick exercise. Draw the Venn diagram for these 4 cents. Which I guess I just did it for you, so maybe go back and watch that part. Copy that. And put the following numbers in the appropriate section. So you get diagrams, nested circles, and there are numbers. -1, square root of 2, 42, pi, 0.8, 1 over pi, 0.999, square root 0.25, near the 8. So put these 8 numbers in the appropriate section. So yeah, that's the first part.